This is stochastic processes, model 8 renewal processes. In the first two lectures, we have discussed renewal functions and its properties, and then we have discussed renewal theorems. There are three important theorems we have discussed in the lecture 2. Today's lecture is lecture 3, Markov Renewal and Markov Regenerative processes. In this lecture, I am going to cover Markov Renewal process or Semi-Markov process, the definition and its properties. Followed by the definition and the properties, I am going to discuss the steady state measures, and I am going to discuss one simple example for the Semi-Markov process. Then the second part of today's lecture, I am going to cover Markov Regenerative process. The definition and the properties I am going to discuss, followed by the definition and the properties, I am going to discuss the limiting distribution. As an example, we are going to discuss the steady state analysis of GM1N Q. First, we are going to discuss the various stochastic processes which consist of DTMC, CTMC, Semi-Markov process and Markov Regenerative process. First, you consider number 1, the sojourn times are exponential distribution. Number 2, every state change represents a regeneration instant. The epochs or points T1, T2 and so on, in which the process probabilistically restarts from scratch, that is, from epoch T1 the process is independent of its past, and the stochastic process behavior from epoch T1 is the same as it had from T0 is equal to 0. These epochs or points are called regenerative epochs or regenerative time points or regenerative instants. So, these are all the two important properties. One is the sojourn times are exponential distribution. The second one is every state change represents the regeneration instant. Accordingly, we can classify the stochastic process. The first one is if both the properties are satisfied, then the corresponding stochastic process are either it is a Markov process. So, based on the time space is a discrete or continuous, we have a discrete time Markov chain or continuous time Markov chain. Whenever the two properties are satisfied, the stochastic process is said to be a Markov process, and the state space is a discrete, then the Markov process is called a Markov chain, and based on the time space or parameter space is a discrete or continuous, accordingly we have a discrete time Markov chain or continuous time Markov chain. If any stochastic process satisfies the property number 2 only, not the property number 1, that means the sojourn times are exponential distribution. If that property is not satisfied, then that stochastic process is called a Semi-Markov process. We are going to discuss in detail about the Semi-Markov process, that is a stochastic process satisfying the property number 2 only. If both the properties are not satisfied, but still not every state change represents the regeneration instant, instead of this there are few state change represents a regeneration instant, then the stochastic process is called a Markov Regenerative process. So, if two properties are satisfied, then it is a CTMC or DTMC. If only the property number 2 satisfies, then it is a SMP. If both the properties are not satisfied, but few state change represent a regeneration instant, then the stochastic process is called a Markov regenerative process. So that we have shown it in the diagram. From the stochastic, from the semi-Markov process, you can have an embedded DTMC by making a proper assumptions that the sojourn times are exponential distribution, then it will be a CTMC. From the CTMC, you can create the DTMC in the embedded. Similarly, from the SMP, you can make a embedded DTMC. By proper assumptions, you can get the DTMC or CTMC. The general case of a semi-Markov process is a Markov regenerative process. If you make some assumptions, then it will be a semi-Markov process. The down arrow means if you make additional assumptions in the Markov regenerative process, then you will get the semi-Markov process. If you make additional assumptions in the semi-Markov process, then you will get a DTMC or CTMC. Whereas this dotted arrows means embedded stochastic process. So from the DTMC, from the CTMC, you can have an embedded DTMC. From the SMP, you can have an embedded DTMC. From the MRGP, you can have an embedded SMP. And from the SMP, you can have an embedded DTMC. So this is a pictorial representation of a various stochastic process based on these two properties. Now we are moving into the semi-Markov process introduction. Consider a system Yt with the state space omega. That means the Yt is a discrete state continuous time stochastic process. Suppose that the system is initially in the state x0 at time t0. It stays there for a non-negative random amount of time, which may follow a general distribution, and then the system jumps to the state x1 at the next transition time instant t1. It stays there for non-negative random amount of time and then jumps to the state x2 at the next transition time instant t2, and the process continues like this. Thus, xn is the nth state visited by the state system at the time instant of nth transition tn. This can be depicted through the sample path. So, sample path means it's a trace. Consider this sample path of semi-Markov process. The corresponding Yt is in the y-axis. The time is in the x-axis. Y-axis is y of t. The corresponding stochastic process has the 4 states. Omega is 1, 2, 3, 4. So at time 0, the system is in the state 1, and the system is in the state 1 till time t1 time instant. At the time t1 instant, the system moved to the state 2. So the system was in the state 0 at time t0, that is equal to 0, and at the time t1 it moved to the state 2. The system is in the state 2 till time instant t2, and then it moves to the state 3 at time instant t2. So from the state 2, the system moves to the state 3 at the time point t3. T2. The system moves to the state 4 at the time instant T3. Now the system is in the state 4, and the system was in the state 4 till the time point T4, then it moved to the state 1 and so on. And the T1, T2, T3, T4 are the time instant. In those time instant, the system is moved from one state to the other states. Go back to the previous slide. The system was in the state x0 at time t0, and at time t1 the system moved to the state x1 and so on. Thus, xn is the nth state visited by the system at the time instant of nth time transition Tn. So, in this sample path, T1, T2, T3, T4, T5 are the time instants, and the system is visiting the states. So, here it is a 4-state model. The omega is 1, 2, 3, 4. Therefore, the system is keep moving into the from one state to other states according to this state transition diagram. We will come back to the same example again. So, this is an illustration of a sample path of Semi-Markov process, and the T1, T2 are the time instant. If Yt denotes the system, if Yt denotes the state of the system at time t, then Y of Tn is equal to Xn. Whenever you observe at the time instant the system, then that is the possible values of Xn. If the Markov property is satisfied at all the transition time instants Tn, then the stochastic process described above is called the semi-Markov process. Whenever the Markov process is satisfied at the time instant T0, T1, T2, T3, T4 and so on, all the time instants. The time instants are nothing but the system is moving from one state to another state at those time instants. So, if the Markov property is satisfied at this time instance, then the stochastic process Y of t is called the semi-Markov process, or in other words it is called the Markov Renewal process. That is, the evaluation of the system after the time instant t equal to Tn depends only on the past history of the system till the time Tn.